No,
Yes,
I'm
awesome.
a hugger.
Okay, awesome.
That's great to have you here. Where have you come in from?
Coming from New York.
Okay, that's not really Silicon Valley, is it?
It's not. It was Silicon Valley before. Spent 9 years at NVIDIA, so love the chips business, and it's great to have this panel that we have arranged today.
I know you're going to take us through what's going on, but one of the things that has struck me is that chips seem to have been a settled thing about 10 years ago. It was kind of Intel for servers, NVIDIA if you're a gamer, Qualcomm, ARM for mobiles. It's completely inside out now.
It's a new golden age for computer architecture, as John Hennessy would say. Intel and the old guard has dominated because really it was an Intel and Microsoft game in the PC business. And they were controlling the whole system from a instruction set level with x86. And now everything in software, everyone's programming in TensorFlow. It's a whole new game, and lots of people can participate.
Well, I don't want to steal your thunder, James. The stage is yours. Thank you very much.
All right. Thank you so much, Azim. All right. It's great to see everyone back at CogX. How many people are attending kind of a repeat year from last year? Awesome. How many people were at this session last year? Okay, awesome. Thanks for coming back. Okay, my name is James Wang. I work for ARK Invest. We're a New York-based investment firm. We're purely focused on the public markets, so not really trying to be touch on VC-level stuff. But we love this field. I love the semiconductor industry, and I'd love to give a high-level overview of kind of where we are with the state of AI hardware, why you should care, and really give you some kind of background knowledge so you can enjoy the wonderful technical presentation that the folks we have coming up right after me. Okay, I think the first top-level question we got to answer is, why do we need better AI hardware? Well, if you look at the reason why we've made any progress at all in AI, yes, it's because of data. Yes, it's because of clever algorithms. But really, compute performance has really gone exponential. The first notable neural network in recent times is AlexNet in 2012. We've progressed from that to AlphaGo Zero, which was able to defeat the world's champion in Go, something that we thought we couldn't do perhaps for another decade. To get to this level, we had to increase compute performance by roughly 300,000x. And you just can't do that using existing technology. If you follow the famous Moore's law, in the span of this period, it would have given you maybe on the order of 10x in performance. So we have to really close the gap from how much performance we need to how much performance we're able to get from Moore's law. And to close this gap, what we need is hardware innovation. Or in this business, it's called kind of computer architecture. So really making better chips using the same old transistors. So what's on the menu if we're building new hardware? Right now, if you're a researcher, if you're someone building AI algorithms, you have a couple of options. It started off with CPUs, which were invented in the 70s. General purpose, pretty useful, but not very fast, not very power efficient. FPGAs came along in the 80s, and those were great for prototyping hardware. But that's also not really designed for AI, although we're seeing some deployments now for inference using FPGAs. GPUs are really the powerhouse today that's driving the performance of artificial intelligence. GPUs were built for gamers. It came out in the 90s. It was for the Xbox. But it turns out that to render 3D graphics, to play Halo or Call of Duty, what you're doing is doing lots of matrix multiplication. And to do linear algebra, which is the basis for AI, it's also lots of matrix multiplication. So GPUs are used today pretty much by everyone to train these neural networks that we're using. GPUs are still not really ideal. They are good for matrix multiplication, but they also do a bunch of other stuff, like graphics, which you don't really need. So Google in 2010 came out with a new type of processor called a TPU, or a tensor processing unit. And TPUs are really designed to put every transistor to work to make these matrix multiplies fast. And now Google has deployed these for use in their public cloud. So that's kind of where we are today. If you look forward for the next decade, kind of every decade we've had something new, there may be tantalizing hints that something new is about to come along again. One of the approaches is actually to use light, using lasers or photonics here to do computation. It turns out lasers can do matrix multiplication. Who knew? The other approach is to use quantum computers, and this really might be the holy grail, the nuclear option for doing really, really massive simulations. And Ilana from Oxford Quantum will go through that in much more detail later on today. Okay, so some folks here are probably in the investing world or try to cover this from a market angle. I think it's good to have an overview of what the market looks like for AI. And the easiest way to break it down, as in many things in life, is just to put it into a 2x2 matrix. The top level view is there are two parts to this problem of artificial intelligence. One is called training, or really creating the neural network. The neural network starts off with completely random parameters. It doesn't know what to do, so you have to feed it a bunch of data and train it. Training is kind of like going to university. You go in, you do it for many, many years. It's very expensive. It's very arduous. And hopefully, when you come out, you know how to do some new things. Once you've trained a neural network, you can actually then use it to perform inference. Inference is using a trained neural network to solve existing problems. When you ask Siri a question, when you load up Facebook and it sends you a recommended video, or when you ask Google Translate to translate from German to English to Italian, all those are using trained neural networks and performing inference so that it will give you back an answer. 10 years ago, none of those services existed. Now everyone is using them multiple times a day. So the data center has really exploded with this demand for inference, which is kind of why Google built its own processor. So these two things on the top are all done in the cloud, and it's all great. But what we really want in the future is to be able to do inference locally on devices, so on your phone, in an autonomous car, in a smart speaker. So that's created this new market called Edge or IoT. And here the chip is a tiny little chip, an SoC, that's able to do a few trillion operations a second, which is pretty impressive. Oh yeah, and one of these boxes don't make sense yet. You kind of really hard to train a neural network on your phone. That might happen in the future, but not really a common format today. So we have 3 different chips. This really creates 3 unique markets. So when people talk about the AI hardware market, you really have to think about it in terms of the 3. They're quite distinct in terms of how much power they provide, how much performance, and how much opportunity there is. For training, at a very high level, this is a high-performance computing problem, which is basically supercomputers. And that market today is on the order of 10 and 15 billion. So if you assume that training is roughly of that size, and accelerators take up maybe 2/3 of that, that's roughly a $10 billion market that we can see today. For inference, these are the endless racks of servers you see in the pictures in Google's cloud. Today, each of those servers is kind of built with 2 CPUs. As more work becomes artificial intelligence, those will not keep up, and you will want to replace them with dedicated accelerators. If you take out a CPU and put in an inference accelerator for $1,000 each, 10 million units gives you a $10 billion market as well. The edge or IoT market is a really new one, and you see a lot of startups going after this because NVIDIA is not dominant in this market. There's a chance for an opening for a new competitor. The cost of these chips are quite low. I mean, they're about the size of a thumbnail. You might charge $10 for these chips, but they're on the order of 20 billion IoT or ARM-based chips sold each year. So if you assume 10% of those become kind of artificial intelligence applications, then you have a $20 billion market there as well. So all up, maybe on the order of 40 billion that we can see right now. It could be much larger, but really 3 different markets and lots of people going after them in different ways. As Azim has said, the silicon kind of space has really exploded. Silicon Valley was born out of creating new computer chips, but we haven't had a lot of silicon startups for a long time because everyone was doing software startups, everyone was doing internet startups, not a lot of people building chips, and that's really changed. And now we have a huge amount of people in this huge contest for a new game, which I'm going to call the AI Chips Hunger Games, because there are not a lot of places to win, and there are a lot of people contesting. It's a bit hard to read. It's not really designed to be read. You can download this from my Twitter account. That way you can see it in detail, but I'll just walk you through at the high level, and we'll break it down afterwards. Basically, the guys in blue are the ones that are the established players, so Alibaba, Apple, NVIDIA, Facebook, and so on. Everyone that is at hyperscale is building some sort of chip to accelerate their own software stack. All the lines in blue are the startups, and these make up the majority. They're from Graphcore, they're from Mythic, and everyone is approaching a different style. I have columns here showing kind of which market they're going after. So a few folks going after training, lots of people going after inference in the cloud. And for IoT, I've broken it out into phone, IoT, and auto because they're now distinct markets. It's not just one big IoT market. And automotive has become a very important market for some of these folks for self-driving cars. Okay, here's a more digestible view of what you're seeing in this chart. The amount of startups, as you can see, absolutely dominates over the number of established companies. It's about 2/3 startups. The target market, most are going after, in the cloud, they're going after inference because it is easier to build an inference chip. But for the most part, half is really devoted to this notion of edge computing. A huge amount devoted to IoT, a good amount to automotive, and as well as phones from kind of Apple and Qualcomm. Product status. Many people are shipping PowerPoints, not chips. We've seen many semiconductor companies that are very hopeful that was going to kill NVIDIA, it was going to kill Intel, and they didn't kill anyone but themselves. But in the end here, we have to really track the number of people that are shipping. And about a third of companies are shipping. But this includes incumbents. So really the ratio of startups shipping is quite low. About half are still in kind of development or sampling mode. In terms of geography, the US, not surprisingly, still dominate the world semiconductor design market, but China is catching up. And you can see that especially in the funding. China receives 40% of all the funding for semiconductor startups, AI startups specifically, which is higher than the US. This is incredible. This chart would not have existed a year ago. Okay, so as we look forward, that's kind of the state right now. I just want to kind of bring 3 themes for 2019 and going forward. One is just this rise of China. I'm not even interested in geopolitics, and the Huawei thing is all very new, but you just can't deny this trend when you look at what's happening with AI startup funding. This is kind of a history. This is a graph from Mentor Graphics they presented earlier last year. And you can see that for a long time, semiconductor funding was quite stable, and then towards 17, it just started spiking. And the yellow part is China. In second Q, they pretty much dominated all the venture funding for AI chip startups. And California, Silicon Valley has become a tiny little bar at the bottom. The result is just a huge boom in the number of companies that's being created. For much of a decade, China had maybe 500 companies who were buying these electronic design tools from Mentor and other folks. And then in 16, 17, it just became this 3x growth almost overnight. A lot of these companies are just 3-people shops, 1 person designing, 1 person selling, and another person maintaining software. But a lot of these are also real customers now for EDA design tools. So China has really become a full force. Perhaps the most striking example of that is where Huawei has managed to end up. A year ago, you couldn't really buy a respectable AI chip from China. Today, Huawei is offering basically a full stack of AI devices, everything from a cloud data center accelerator with 200 trillion operations a second, down to a tiny chip with less than 1 milliwatt of power that would fit inside an Apple AirPod. So when you ask a question to a device that's only battery operated, that even has AI capability. This is now available from a Chinese domestic company, which is pretty unprecedented. The number 2 theme that has become really clear is vertical integration. And this is interesting because in the last wave of computing in the 90s and 2000s, everyone knew their place in the supply chain. Intel built CPUs, Microsoft built operating systems, Adobe built applications. Everyone stood their lane, and no one was competing with each other across stacks. And that's just not true anymore. In 2010, Apple started designing their own CPUs. This was just extremely not on trend because Apple had been procuring CPUs from Motorola, from IBM, from Intel, but now they were designing their own CPUs for the iPhone 4. And pretty much Apple, by the iPhone 5S, had the fastest and first 64-bit mobile CPU in the market. So this is an example where your customer, if you're a chip designer, becomes your competitor. And this is a dynamic where you can't really win because when they insource their own components, they're not really having a discussion with you about whether they're going to buy your components. In 2016, Google continued this trend by designing their own TPU. They saw that this inference workload was exploding. Everyone was doing voice-based search. And when you do voice-based search, running that on a CPU is just too performance intensive. So they designed a processor that's designed to basically accelerate those kind of operations in the cloud. They built the first version. They're now on the 3rd version. They're still buying from NVIDIA. They're still buying from Intel, but they're certainly not buying as much as they used to. Probably the most exciting and surprising announcement came this year with Tesla. Tesla announced that they were also designing their own silicon, and they built basically a full self-driving computer for the Model 3 and the Model S. Using this processor, they were basically able to kind of accelerate the go-to-market ahead of NVIDIA by maybe 3 to 4 years. NVIDIA has a very powerful system that does this, except it's 500 watts and it's in the size of a briefcase. Apple's computer is more like the size of a lunchbox. So because they can optimize for their own neural networks, they can actually build chips that's very effective for themselves. For a silicon startup, this is slightly concerning because some of the world's largest customers are now no longer part of your addressable market because they've insourced this design. But with a 40 billion market, I think there's still plenty of opportunities. You just have to be careful about who you can depend on as a long-term customer. You don't want them to be the kind that kind of eventually insources their silicon. The last thing that's notable is that optical computing, or computing using lasers, is really making a comeback. You saw that table with over 60 companies. 7 of those companies are using photonics as the basis for computation. Photonics is exotic, but it's not actually a new technology. It was invented in the 60s in Bell Labs, and it's been kind of refining itself ever since then. It never caught on because Moore's law was just too powerful. It grew exponentially, where photonics, you really had to kind of deal with a lot of messy hardware details. But there are really some advantages with photonics. Photons use less power than electrons. Once you generate them, they just keep on going. You don't have to kind of keep feeding the power. These companies also leverage the existing semiconductor supply chain so that you don't have to build out a whole new factory like a TSMC for lasers. You can just integrate these onto existing silicon process. And these companies, which really is extremely diverse, like it spans Lite-On from France, we had them on last year. We have Optolysis from the UK as well. We have Fathom from Canada. These companies, some of them are already in customer trials, which really shows that this technology is not just some faraway technology that we're not sure how to evaluate, but they're actually likely to work, and we'll get results in the next 2 years or so. Okay, so kind of circling back, this is the high-level slide. I just want to kind of end with a reflection, which is the semiconductor business is highly unrelenting. NVIDIA almost went out of business because they built one incorrect chip in their early days. And as you look at the table, this is very encouraging, but obviously, I think not all of these startups will make it in the end. But that's not always bad news. The companies in blue, the incumbents, some of them do not have very well thought out AI roadmaps. They do not have good silicon for accelerating these processes, and they will need all the help they can get. So I think over the next 3 years, you will see a lot of the companies in green be taken in and absorbed and acquired by the companies in blue, and that would be quite a satisfactory conclusion. But of course, that's not what they're hoping for. They're hoping to change the world, and I think given the size of the market, given all the applications that's exploding around us, every day we're finding a new use case for AI, I think there's a real good chance that one of the companies in green, one of the startups, perhaps one of the companies presenting today, will be the next ARM, Intel, or NVIDIA. All right. Thank you. So speaking of those companies, we have one of them coming on stage right now. Nigel Toon is the CEO of Graphcore, based in Bristol. His company, lastly, was acquired by NVIDIA, and I think the architecture presented by Graphcore is one of the most compelling I've seen, and one of the few people, I think, in the world who can give Jensen a run for his money. So please welcome Nigel.
Thank you. Thank you for those kind words. So, no pressure, right? How many did you say there were? 63 companies in this space. There were a similar number of Wi-Fi companies that were funded as well. There was only one of the startups that managed to go public and remain independent. So, let's not underestimate the challenge in front of all these companies. So, I'm going to save you from having any slides. Maybe that's disappointing for some of you, but I'm going to try and get you to do some of the work. So let me ask you a question. How do you think? I mean, think about how you actually think. So imagine you're trying to recognize a cat. Can you describe what it is you're doing that would actually happen in your brain to cause you to recognize a cat? It's kind of not obvious, right? We think we're very good at explaining and post-rationalizing how we describe and how we solve problems, etc. But the reality is there's something very special going on here. So take that other example. How do you make a decision? You probably all hear made a decision recently. Maybe it was an important decision. Maybe you're changing jobs or moving house or something. And probably you look back on that and you think, well, I can post-rationalize how I made that decision. I went through these logical steps. But could you write a program that would allow you to make decisions successfully, even quite narrow sets of decisions? Could you actually write a program to do that? Or would it actually involve some level of intuition, some hidden magic somewhere that's causing you to make these decisions? I often find when I make difficult decisions that there isn't enough data, there isn't enough information around to make the decision, and afterwards you sort of post-rationalize why you make the decision, and you sort of list out all the reasons why you actually did what you did, but actually a lot of it was intuition, which kind of implies there's a black box somewhere in the middle of this that is how you're actually deciding, how you're actually thinking. There's lots of dots, and you're joining the dots together kind of magically inside this black box, inside this brain of yours. And so, I think it's really important to realize that the way we think is not necessarily the way we write programs. Today, we write programs, and programs are becoming very, very complicated. And we do those in a sort of linear fashion. So this morning, I was a bit late getting here, running through the rain. I think we've all got wet. I actually was over at Stratford, and I was invited to meet Theresa May. I think she's still our Prime Minister, but it was kind of surreal to be involved, meeting this person who's obviously in her last few weeks in office. But when I say the words Theresa May, I don't know how many of you here are from the UK. There's probably all kinds of triggers that go off in your brain. You'll think of Brexit, compromise agreements, maybe Boris Johnson or leadership elections. All these parallel triggers go off inside your brain. And it's amazing how that happens. You say a word and it triggers all these responses, especially something that's kind of quite well known or quite emotive in terms of the way you're actually thinking about things. So we're not thinking in straight lines. We're not thinking in sort of linear progressions. We're not thinking in terms of steps. Lots of stuff is happening in parallel inside our brains. Now, that doesn't necessarily mean that we should try and build computers using exactly the way our brain works. We don't make aeroplanes that flap their wings. We use different materials and we design things in different ways. The best way to build computers today, the reliable method, the method we know we can build in high volume, is silicon. So what we really need to think about is how do we change the way we build a silicon chip to be able to work more like our brain, to work in a way that is actually going to allow us to create these machine intelligent systems. So 75 years ago, the very first electronic computer was built. It was built here in the UK. It was built at Bletchley Park. It was called Colossus. Nobody ever knew about it because it was kept secret. It was a wartime secret. It was used to crack the really difficult high command codes. The Enigma codes had already been cracked, and this was a much more complex system that was designed to really crack the high command codes. And it came online just before D-Day, which we've just been celebrating 75 years ago, and it was able to actually crack all of the German high command codes, so the Allied forces knew exactly what the Nazis were thinking and what their plans were. And it had a very simple software interface. It was actually plug boards that you actually programmed the system with, so it was actually programmable. You could change the program on the machine. And since that time, we've obviously built really, really complex software, what we think of as algorithms, or describe as algorithms. The software has become incredibly complicated. It takes teams of people to write the code. One single person probably can't understand how the system is actually working. You need really complicated verification teams to make sure the software is actually working, and even then you seem to get bugs all the time in your software. So something really amazing happened just a few years ago, and James referred to it. AlexNet was the first time that a machine learning system was able to produce a result that was more accurate than an actual program. So for image recognition, AlexNet built a neural network model, a deep neural network model, that actually produced a result that was more accurate than any algorithm that had been created for doing image recognition. And it was a fundamental moment of a fundamental breakthrough in terms of machine learning having enough data, having enough compute to be able to build a neural network model, a deep neural network model, that would actually be better than software. And that's the fundamental thing that's going on here in terms of machine learning in its broadest sense and what we think of as AI. It's not some special party trick where we're recognizing cats. This is really fundamental. We're moving from a world where we've told computers what to do step by step in a program to a world where they're going to learn from data. And the machines that we need to actually allow that to happen and to be efficient at doing that need to be different than the machines that we've built for the last 75 years that take a software program, process it, and give us an output. It's not just linear algebra, it's not just maths. That's a hugely important part of it. Convolutional neural networks, everybody's heard the term. What does it really mean? Well, when I went to university, convolutions basically is filtering, right? You're taking some data, you're filtering something from the data to extract some information from it. And so it's layers of filters that are filtering out information from the data. We're building up a hierarchical understanding of the data, what we call dimensions of information about the data, to be able to understand from an image what actually is the object inside that image. So give me 1 million pictures of cats, I'll build a model that will be able to recognize cats. Hopefully it doesn't just recognize the cats that it's learned in the 1 million images. Hopefully it does something called generalization and actually generalizes and allows us to actually learn what cats generally look like. But it's still not quite the same as how we do it. It's kind of a bit like the frontal cortex of your brain, but it's not completely correct. Okay, we're recognizing the object, but are we then able to use that understanding to be able to recognize what a dog looks like or an animated picture of a cat? It's amazing. You show a child, you show them a cat, they'll very quickly learn what a cat looks like, and then they'll see a cartoon on the television or on their iPad, and they'll be able to recognize an animated cat very, very quickly without ever being told that that was a cat. So this ability to transfer learn, this ability to make these leaps is something that we can do. So we know the systems that we're building today, the machine learning systems that we're building today, are still very, very simple. They're not yet anywhere close to the kinds of real intelligent systems that we'll be able to build at some point in the future. And what's holding people back, and this is really what we learned when we started Graphcore, talking to all of these leading innovators in machine learning, is the key thing holding people back is hardware. The kind of machine learning that we have today is really enabled by the hardware that exists today. So GPUs and TPUs, for that matter, allow us to create the kinds of machine learning systems that we have and are being used today. But to be able to make the next breakthroughs, we need something more. We need something different. We need something which is much more powerful. And the key to understanding that is it goes beyond just the arithmetic. Yes, you need lots of arithmetic. But what we need to be able to do is to think more about the data than thinking about the arithmetic. The thing that you notice if you follow computer architectures is the architectures follow the data. Why is a GPU different from a CPU? Well, because the data's arranged in three-dimensional blocks, X, Y pixels and a Z dimension, which represents the color information inside your picture. And so GPUs are very good at taking large blocks of data, doing some very complex arithmetic on that, and creating some new results. So take this block, paint those pixels blue, and put them back in the screen. That is what GPUs were designed to do. So they have the arithmetic, but they work on large blocks of data. And that's not how we actually need to deal with the data. The data we're trying to deal with is very, very different. The data structures that you're creating when you build a machine learning model are very high dimensional. And what that means is the data is connected to other sets of data, but it's not necessarily connected to all the other data. Think of a social media network. So you've got certain friends and they've got certain friends, but you don't know who all their friends are. So there's lots and lots of different levels of connections inside that. It's like the neurons and synapses in your brain. You've got different levels of connection, and you're building up this very high-dimensional picture of the underlying information that inside the data that you're learning from. And to be able to process on that data, what we actually need to be able to do is to access that data much more in parallel. So most CPUs today, GPUs today, they have a single big block of memory that sits next to the processor, and there's a high-speed connection to talk to that memory, and so there's big pieces of data being pulled into the processor. That memory interface, that bandwidth on that memory interface has got wider, it's got faster. The latest GPUs are using things called high bandwidth memory that deliver about 900 gigabytes per second of bandwidth to the memory, which is great, incredible technology to be able to make that happen. But it isn't anywhere near enough. What we actually need are thousands of memories connected to the processors. We need to be able to improve that memory bandwidth by a factor of 100 at least. And so it's really the memory structure that becomes the critical piece inside the processor architecture. It's really the memory is the driving factor, has to drive the architecture. And some of the startup companies that were referred to earlier are thinking about this. I think Graphcore is one of the few that has really put this into action. If you can have thousands of processors connected to memory, the next problem you've got to worry about is how much of the energy are you spending on accessing that memory versus doing the compute. If you look at a CPU, the pipeline that is fetching the data from the memory, keeping the caches full, getting all the data lined up, making sure that it doesn't miss in the cache pipeline, all of that is burning most of the energy inside a CPU. Very little of the energy is actually going to the arithmetic inside the CPU. So in a world where we are power density limited in silicon design today, what we need to do is to think much smarter about how we actually do that. We can't really have caches. We can't really have memory misses. We've got to have the data being local to the actual processors. And so we've got to order the data to be in the right places at the right time and get rid of all of that hierarchy and make it super simple so that all of the energy can go on actually doing the arithmetic rather than doing the data collection. And if you can do that, then you can roughly double the amount of work that you can do for a given piece of power consumption. That's what we've been able to do inside Graphcore. And what we've also been able to do is to have thousands of processors connecting to thousands of memory, and which gives us 100 times the memory bandwidth compared to the conventional approaches. And what that means is that we have much, much more ability to do things in parallel, many more parallel tasks running inside the machine. But that alone is not enough. There was a really clever, very modest engineer who worked in IBM labs in the 1960s. His name was Edward Rent. he looked at how logic and the inputs and outputs to that logic were actually related to each other. And what he found was there was actually a rule, a law, which became called Rent's rule, Rentian scaling, it's called, where the amount of interconnect goes up on a power law compared to the number of logic cells that you have inside your chip, for example, or the logic that you have in a certain area in your chip. The interconnect to that area is a power law of the amount of logic you have inside that chip. So it's a fundamental part of chip design. It's a fundamental part of FPGAs. Anybody here who's used an FPGA will know that you always run out of interconnect inside an FPGA, and it's basically because of this Rentian scaling problem. What's really interesting is that your brain has exactly the same scaling. If you look at neurons or collections of neurons and the synapses that connect to those, the connections to those neurons goes up on a power law depending upon how many neurons you capture inside the group. So if you're going to put down lots of processors, the real issue you have to deal with is not just how do I get the data to be in the right place, but also how do I organize all of this communication that has to go on between the processors. I need to be able to account for the fact that as I have more and more processors, I need to have even more, on a power law basis, communication between those processors. And if you look at any parallel processor that's ever been built in the past, none of them have anywhere near enough interconnect inside them between the processor cores. So again, that was something that we looked at very hard and we built into our architecture. So what we built, I have one here in my pocket. Not that you can see, I can show it to you afterwards. So here you have the world's most complex processor. This is 24 billion transistors. It's built in 16 nanometer technology. We're working on a 7 nanometer version, which will be even more complicated than this. It has 1,216 independent processor cores, each of which runs 6 program threads. So that's over 7,000 programs, independent programs that are running in parallel on that machine. Each of those processor cores has its own full-speed memory. The processor cores run at 1.6 gigahertz each, and they produce 100 gigaflops, over 100 gigaflops of compute capability. So that gives us over 120 teraflops, actually 125 teraflops of performance, floating point arithmetic. Floating point is very important. I won't go into the details of that here. There are some things on the web for our CTO that will go into the arithmetic issues. But we've got huge amounts of computing power inside this device. But one chip on its own is not enough. So we've built interconnect into this chip that allows clusters of these processors to be connected together. And we've built an IPU gateway that allows us to build clusters of 4,000 IPUs. So that is, I wrote it down because I couldn't remember, 30 million parallel programs running on a cluster of 4,000 IPU processors, all working in parallel on a single problem. So that's what we're doing at Graphcore. We've raised a ton of cash. I think probably more than 10% of the money for Europe that, most of the money for Europe, I would say, that James has talked about. And we're really working and trying to allow innovators to create the next breakthroughs in machine learning. Thank you very much.
Thanks so much, Nigel. Thank you. All right, thanks so much, Nigel. Nigel's painted a very vivid kind of image of what a high-end processor looks like in the future for the cloud training, cloud inference, and they're really going up against NVIDIA. Upcoming next, I'm very happy to have Mike Henry, the CEO and founder of Mythic. Mythic is going after that third market that we looked at in the beginning, the IoT, the edge market. Here, the amount of power that is available is just in the watts, maybe in the number of milliwatts, and they're using something very unique technology to bring very high performance, trillions of operations in something that can fit inside of a smart speaker, inside of a earpiece. Please welcome Mike Henry.
Go. All right. So thank you for the introduction. I don't have the ability or mental organization to give a fascinating 20-minute talk without any slides. Maybe a little more experience and I can do that, but what you'll get instead is a carefully choreographed 1 minute per slide PowerPoint presentation. So a little bit different. All right, so Mythic is pioneering analog compute for edge AI. And so I'm going to spend a little bit of time talking about what analog compute is, because it is a different type of technology. It's one of the new up-and-coming emerging technologies, like that was mentioned earlier. And we'll talk about the product and how it fits into the market and how we're able to carve out some really nice niches where analog computing can provide a tremendous amount of value to customers. So this is similar to the numbers you saw earlier. You know, a lot of analysts are putting out numbers that roughly fall in the same ballpark here. You know, we're looking at a tremendous $30 billion opportunity, at least, for AI silicon. And eventually it's going to break out into these three domains here. You have your training hardware, you have your data center inference hardware, and you have your edge inference hardware. And actually, when we talk to customers, we're seeing, you know, we'll hear customers say something like they spend about 5 times as much on inference and deployment hardware as they do on training hardware. So even at the small scale, customers, we're seeing these kind of breakouts emerge. Now, Mythic is solely an inference company, so we're playing in the red and the yellow here. And I'm actually going to spend a little bit of time, though, talking about the red market, the edge inference market, because that's actually the market where there are a lot of different niches that those 63, you know, semiconductor startups can carve out for themselves and have a nice place to play in where you're not worried about getting bulldozed by NVIDIA. So right now at the edge, we are seeing an insatiable demand for compute. So we're looking at customer workloads now that make ResNet 50 look like a toy. You know, ResNet 50 is kind of the gold standard benchmark that people are giving for their chips, and the new things emerging make that look like a tiny, tiny network. We're also dealing with a rapidly changing software ecosystem. So last year, 3x3 convolutions were all the rage. In ResNet 50, 3x3 convolution neural network, or the bulk of the works is 3x3 convolution. And now, even a week ago, Google comes out with this new network that, in terms of accuracy, blows ResNet 50 out of the water. And it's actually made up mostly of depthwise separable and dilated convolutions and these other things that don't fit in that 3x3 world. So for those AI chip startups that are building 3x3 convolution engines, now all of a sudden their chip starts looking a little bit obsolete, and it literally just takes a year for that to happen. So we're dealing with a rapidly changing software landscape. We're dealing with this demand for having larger models that can store more information and handle all those edge cases that emerge when you're doing things like self-driving cars and security systems and anomalous behavior detection. And so the best quote I heard was from Andy Feldman, a very colorful CEO of Cerebras, who said that the largest problems you see today should be the smallest problems that you solve for tomorrow. So everything that we see today, just assume 3, 4, or 5 years from now, it's going to be 10 or 100 times bigger, because that's what we're currently seeing. Now, on top of this, oh, that's weird. On top of this, we're dealing with something that we haven't seen in the last 30 to 40 years. You know, the incredible rise of computing and electronics that we've seen since the 60s and 70s has really been powered by Moore's law scaling. And you know, despite the best efforts of TSMC and Samsung now, who are the only two foundries going below 10 nanometer, you know, they are pushing out 7 and 5 nanometer. What we're seeing is exponentially increasing costs. We're seeing diminishing returns as you go to each of these newer nodes. And I'm quoting someone else here, and I can't remember who said it. We're at 5 nanometer now. There's really only a few numbers left between 5 and 0. So how are these all-digital systems going to respond when all of a sudden the engine that powers them runs out of steam? This is why we need a new breakthrough in chip technology, something that actually resets the clock on Moore's law. And this is actually not new to the semiconductor industry. You know, before NAND flash, we had big spinning hard disks, and they They really pushed the capacity limits on them, but eventually you hit a limit in size. Somebody invents NAND flash, and now you can have gigabytes on your smartwatch. And same with RF CMOS. What used to be big, bulky PCMIA Wi-Fi cards, now, again, inside a smartwatch. And that's all because of RF CMOS techniques. And CMOS imagers. Getting a CMOS-compatible image sensor replaced those giant, bulky analog cameras that used to exist. So, this technology has happened before, but what's never happened before is this kind of breakthrough technology for doing compute. Compute has always been sacred. It's always been digital, highly accurate. But this is the paradigm that Mythic breaks. So I'm going to dive a little bit into analog computing here and how it translates into the circuit-level technology we have, and then I'm going to take a step up and show our chip architecture. So this is a matrix multiply. This is 99.99% of the math of inference. And unlike training, which needs to be floating point, inference you can get away with lower precision. So the training process produces these weights. In a state-of-the-art model, you might have anywhere from 20 to 50 million weights, sometimes even bigger. And this is a major bottleneck. You want to fit these all on chip because going off chip kills your performance and it kills your energy efficiency. So how do you fit 50 million or 100 million values onto a single chip that's small and low power and able to go at the edge? Well, what we do is we actually store these integer 8 values on flash transistors. But we go a step further and we actually store an 8-bit value on a single flash transistor. So that is 50 times denser than SRAM for storing weights. So that's how we can fit giant, powerful models onto a small chip. But it does not stop there. Once you program a flash transistor with an 8-bit value, you've effectively turned it into a variable resistor. You've changed the resistance of it programmatically. And now you take that flash memory array that's sitting inside our chip, and you start pumping currents through it using DACs, and you start capturing the values using ADCs. Well, you've turned that storage array now into a matrix multiplying engine. You're able to do the multiplies here, and the values all accumulate on the vertical wires, and those are the accumulates. Multiply, accumulate, the engine that powers AI. So analog compute not only gets you incredibly dense storage on chip, but it gets you computation inside the memory, and it gets you 50 to 100 times lower power and significantly higher performance all at the same time. And then we wrap this up into a digital array, and then we have conventional processors attached, and we have conventional memory attached. So we also have a digital system attached to it to do all the other things that aren't matrix multiplies. And the hardware here that does the digitization and also has compensation and calibration. When you take a picture with your CMOS image sensor, it looks like total garbage. There's a lot of variation that happens. There's a lot of manufacturing and environmental variation. But they have compensation techniques that cancel all that out and get you a clean 8-bit image with your CMOS image sensor. So we actually apply similar ideas to get reliable 8-bit computation out of the analog compute array. And that's actually a lot of our core IP that took many, many years to figure out. So Mythic was started in 2012. It's just me and my co-founder in a tiny office at the University of Michigan. And a lot of talk has been given about how a huge amount of funding is going into China and all these startups are spinning up. But I still think that the US has that secret sauce, which is government funding for thousands of different ideas all concurrently, planting 1,000 seeds and seeing what grows. And so we really benefited in the early days from this government-funded research. Spent about 4.5 years on government-funded research. And then when we actually proved enough, then we got to experience the other great thing that powers innovation, which is Silicon Valley. And Silicon Valley isn't just great because, yesterday I was sitting by the pool and it was 85 degrees and nice and sunny and warm. It's also great because a few people who proved out a concept with government funding was able to then quickly ramp up a company. So in the last 3 years, we've gone from 5 to 95 people. We've raised $86 million. I don't know why I had to look at that number. I should know it. We raised $86 million, and now we're steaming ahead towards production. So those are the kind of things that you see in innovation that just pumping a lot of money into venture capital is not going to get you. So we've already talked a lot about training versus inference. I think there's one main point I want to make here. Training, you're selling something to every developer, and those developers typically have very high salaries. And if you can tell Facebook we're going to cut training time in half or a third for your developers, they will pay a fortune for that system. There's really no practical limits on cost. Power is just OpEx to them. So it's all about system level design. It's about keeping memory close to the processing, but there's few other limits. Inference is a little bit of a different beast, especially at the edge. When you're at the edge, cost and power matter incredibly. A lot of people making smart cameras don't want to spend more than $10 on a chip. Power has to be under a watt, and your software has to really easily plug into the existing system. And and the same thing actually goes for the data center too. Cost and power for inference matter a lot in the data center as well, because if you're going to have to scale to hundreds of millions of users, those CapEx and OpEx costs really start adding up. So this is what the Mythic product looks like. It's a chip with a PCI Express interface to connect to the host, and that's it. There's no external memory, no external DDR memory needed. All of the weights of the neural network are stored inside the chip in an integer rate format. And here's another sneaky benefit. We're in a standard 40 nanometer process. Now, if you look at the wafer costs of 40 nanometer and the mask cost of 40 nanometer versus 7 nanometer, well, we're actually going to be able to use cost as a significant bludgeon because we're in a significantly cheaper process, getting far better performance. And when it was brought up, there were 60 Wi-Fi chip startups. The one that won was Atheros, and the way Atheros won was cost. They won the cost game. And I truly think inference is going to be a cost game. It's going to, you're going to need good software compatibility. You need to support all the latest, greatest neural networks, but it's going to be a cost game. So I'm just going to talk briefly about our philosophy behind our chip architecture. So this array right here is the analog compute array. It gives you a lot of just raw vector matrix math. There's no fancy 3x3 convolution accelerators, no Winograd this or that, just a lot of raw compute power to keep up with all the changing trends in neural networks. And then we have a Nano Processor, which is RISC-V. It has a digital vector engine to handle non-matrix operations. And then a bunch of conventional SRAM to store intermediate values and store program code and things like that. And it forms a tile, and now we can fill a chip up with these tiles, and these tiles can talk to each other. So it's a similar idea to what Nigel talked about, but much smaller scale, targeted for edge inference. So our first production chip is going to have 108 tiles. So that means it has capacity for 108 million weights. Each tile stores 1 million weights. I'm going to skip this slide. We're also, just having a simple chip in 40 nanometer with tons of availability at the foundries lets us do a lot of product iterations quickly. So we'll have a single chip to design into things like cameras. We're going to have an M.2 accelerator card. Those are going to be useful for edge deployments, but also interestingly, Facebook is looking at M.2 to power their server inference because it can plug right into their CPU, their Xeon systems. And we're also going to have some big compute cards. These are really targeted for on-prem server. For example, if you have a bunch of cameras feeding into a box, it can be used in there. But it could also be a good candidate for the data center as well. So I talked earlier about how there are lots of niches developing in the AI hardware landscape. Training in the data center, that's I wouldn't call that I wouldn't say there's a lot of niches there. Even data center inference, 95% of the workload is done by the same 8 or 9 customers. But when you get to the edge, though, you have now a tremendous opportunity, and you have lots of different customers with lots of different interests in mind. And what we're really targeting here is people who want to do really large, powerful models, and they're very cost and power constrained. So this is not like, oh, I implemented a cat versus dog detector on my Snapdragon, and that's good enough. It's not like the Nest camera where it works 20% of the time and they don't care. This is people who like enterprise systems where they need to have really high accuracy, really powerful models, They want to put it into thousands, tens of thousands, hundreds of thousands of cameras, and they're very constrained by cost and power. And so that's where, that's what we're calling the high value edge, where they're willing to spend $10 or $20 on a chip to run something much more powerful than ResNet 50, HD resolution, 30 frames a second. And that, in and of its own, is a multi-billion-dollar market. And we can pull into that on-premise aggregation. So maybe you have, maybe all the server racks in the back of a Walmart have all these, I don't know if you have, I don't know what you guys have, or maybe you don't know who Walmart is, but you have thousands of cameras in a store, and they all feed into a bunch of server racks in the back of the store. That's what we call on-premise aggregation, and that's becoming its own big trend, and that's where server cards can really be useful. Cloud edge and data center are areas that we think there can be a lot of opportunity there, but we do see a big difference in terms of accuracy and software requirements. So the software requirements in the data center are much more strict. So it's not a great place for a startup to play unless you're very well funded. So, all right, I'm going to skip to this slide. So this is what category creating looks like. When you invent new technology that creates a new category, where you're able to deliver a tremendous amount of energy efficiency, far better than the competition. You're able to deliver high performance, low power, low cost enough that it can go into cameras, it can go into consumer products. You can pack thousands of them into a server, and it's not a large expense. This is what we created here at Mythic. And we are going to be sampling this later this year. So this is literally actually a week away from production silicon going out for manufacturing. And I'll just talk briefly about software here. So I think this top part is basically table stakes at this point. You need to be able to interface with PyTorch. You need to be able to interface with Caffe. You need to be very seamless for developers. This bottom part here is actually where I think there's a lot of additional room for differentiation if you're an AI chip startup. So Graph Compiler, being able to automatically generate machine code so users don't have to write low-level firmware. That's very important, especially because these networks are evolving very fast. And this part here, right, is a big opportunity as well, the optimization suite. So making it really easy for customers to push their neural networks into the integer 8 domain. And also, when you're talking about compute and memory, you're talking about making things pack nicely and efficiently. You're packing these neural networks into these compute and memory blocks. So having it really easy for the customer to automatically do things like neuron-level sparsity and trim the network down so it packs very efficiently is going to be a huge opportunity for people pursuing compute and memory architectures like us. So this is going to get a lot of a focus. And the other thing that we really stress is a very easy driver. When you're plugging into systems that already have complex software stacks, like a security camera, you can't all of a sudden bog down the host system with a bunch of new routines. So we offload everything to the IPU, and we just focus on very simple commands, load a configuration, set the buffers, and run inference. And our IPU takes care of it all. By the way, Nigel, I don't know if you trademarked IPU because we're also using it. So this is Mythic in summary. We're delivering a solution that's critically important for embedded applications, and we're targeting a range of industries. And we're targeting a solution that can run large, powerful models. We're giving a lot of raw matrix compute to keep up with the latest state-of-the-art. And we're targeting a solution that fits in the budget both of in-device, on-premise, and data center large-scale deployments. And this is breakthrough technology that this is all based on. Breakthrough technology that is production ready. So this puts us on a totally different roadmap from everyone else because we have many avenues for improvement, whether it's new analog techniques, new non-volatile memory technology, new software, new digital approaches, things like that. We have this really rich roadmap for improvement. When if you're thinking in all digital, you're really kind of stuck at the end of Moore's Law. You're going to be looking, saying, where do I get my next improvements from? Well, we have all this opportunity to improve analog computing and get even more 10x gains over the years. So, thank you for listening, and thank you to CogX for hosting me here. We're going to be rolling out a new website in about a week when we announce our latest funding round, and there'll be a chance to sign up for newsletters and get more information there. So encourage you to check out our website in about a week when we have the new one rolled out. And we'll be here answering questions later on during the panel session as well. So yeah, thank you everyone for listening.